Good morning, all of you that are present here at the Frontiers in Nanoscience series of seminars. Can Gonzalo please confirm that you can hear me?
Yes, we hear you.
Thank you. Thank
No
you. My name is Ivan Suller. I'm from the University of California in San Diego. I will introduce the speaker, the first speaker in the series of seminars. Professor Roldolfo Miranda will be the master of ceremonies, and he will manage the question and answer. You will be able to ask questions anytime. Please raise your hand in the Zoom. That is at the bottom of your screen somewhere. Professor Miranda will allow you to speak, and please remember to turn on your microphone. Otherwise, we cannot hear you. So every time you want to ask a question, remember to turn on your microphone. Now, for me, it's a great pleasure to introduce this series of seminars. I'm the president of the IMDEA Nanoscience, which is a source of pride for me. Those of you that know me, you know that very seldom I put on a tie. There is a place where I put on a tie, which is when we have the meetings of this foundation. Now, the reason that I put on a tie this time is not only because that I'm acting here as president of the foundation, but because this year I've watched this whole institution in there, for those of you that don't know it, how it evolved. And I was there in the beginnings of it, in the gestation of it, which seldom you are in the gestation of anything. And not only that, but for me it's a great pride because this is exactly 13 years after the birth of this institution, which is the bar mitzvah of this institution. And therefore I want to say that for the bar mitzvah is when the institution goes from being a child to being an adult. So IMDEA is becoming an adult. And so all I can say is to all of those of you that are part of IMDEA is Mazel Tov. And I hope that you guys are all will continue doing as well as possible from even under this special condition. Now, I learned a lot from the father of this institution. The real father of this institution was Professor Miranda, who, as far as I'm concerned, is the genius that is behind this whole institution. And I'm very proud of having been asked to actually participate in a small part in part of this adventure. Now, this seminar series was motivated in large part by Bonifacio Vega, who is the man with a lot of hairs in your screen there, in the middle of your screen. And the series was motivated by him, and this will hopefully be a very successful series. Now, today's seminar is actually, it was chosen a very great first speaker for this seminar. The first speaker for this seminar is Dr. Javier del Valle. Dr. Javier del Valle is graduated from the Universidad Complutense, which for those of you that are not Spanish, you don't know, but Universidad Complutense is one of the biggest universities in the world, probably, and certainly in Spain and in Europe. What impressed me about Dr. Del Valle is that he has done a lot of work on very simple ideas. And even for his thesis work, which was done under the guidance of Professor Vicente and in collaboration with Elvira Gonzalez, they have developed a device, a unique, very simple device, which once you know how it works, it's obvious, but before you know how it works, it's not obvious at all. It's something called a ratchet, whose sign is controlled by the amplitude of the drive. So you put an AC signal on something, and the device gives you a DC signal out, and the sign of this DC signal is controlled by the amplitude. I don't think there is any device known to man that does this. So this was his thesis work. After that, Dr. Del Valle came to postdoc in my group at the University of California in San Diego, where he was funded by the US Department of Energy by something called an Energy Frontier Research Center dedicated to neuromorphic computing, which is basically the image behind me, which is we are trying to put together a machine that works like the brain based on solid state devices. And he was there at the start of neuromorphic computing. And just to show you illustrate one simple device that he actually came up with, and which actually worked marvelously, and it's characteristic of Dr. Del Valle's work, is he made up a thermal electric neuron device which works on two phenomena combined together, which I'm sure he will talk about it. But this was one of the highlights of the work that appeared in Nature just very recently. So I'm very proud of this, both of the bar mitzvah of the India and also of the fact that the first speaker is Professor Del Valle, and he will tell us about neuromorphic computing, and then I can take off my tie. Thank you.
Thank you, Ivan, for the introduction. Let me prepare this. Can you see it clearly?
Sure.
Okay, so yeah, thank you, Ivan, for the introduction, and thank you to the IMDEA direction for inviting me to give this first talk of these global seminars. This talk, now I'm at the University of Geneva, but this talk is mostly going to be about what I did as a postdoc in San Diego, that I'm now continuing this research in Geneva. And I would like to start first by thanking the funding agencies, as usual. So the people who pay me now is the Swiss National Science Foundation with an Ambizione fellowship. And the people who funded the research at San Diego was the US Department of Energy with an Energy Frontier Research Center. So what I'm going to talk today about is, I'm going to show our research in that field, but not only that, I'm going to start by introducing the field of neuromorphic computing, because I know it's new for many people. And I'm going to give I'm going to present it and show what's the state of the art, what has been done so far and what has not been done, what needs to be worked on. So this is, I would also like to acknowledge the collaborators. As I said, this was done in Ivan's lab in San Diego, collaboration with other postdocs and students there. It was very nice to work with them there. And now I'm continuing in collaboration with Jean-Marc's group in Geneva. And I will show you some experiments, some synchrotron experiments that was done in collaboration with Electrical group in San Diego. Some simulation that I will show you was done by Marcelo Rosenberg's group in Paris. And we also have some other ongoing collaborations with Duigu Kusum, who is an engineer in San Diego, some TM with G-Meizu group in Brookhaven, and we also collaborate frequently with Javier Ramirez from Universidad de los Andes. So this is an outline of my talk. As I say, I will introduce first the field of neuromorphic computing, why is it important, and then I will give you a detailed account of what has been done so far in using membristors as artificial synapses. And then I will move on and I will show our research in this, in the voltage trigger insulator to metal transition. Every time you see IMT, that's going to mean insulator to metal transition. And then I will show you an example of how can you use this voltage trigger insulator to metal transition to do something that might be useful for neuromorphic computing, which is a thermal memristor. And then I will finish with some prospects, what's coming next. So why neuromorphic computing? So you have the worldwide, every minute you are producing almost 50,000 photos that are being uploaded to Instagram. Before the pandemic, I don't know now, but this is from a year ago, there were 150,000 Skype calls happening simultaneously and over 500,000 Facebook comments. That's every minute. So if you add up to a whole day, you have that every day we produce 2.5 exabytes of data. And this is only going to get worse because this thing of the Internet of Things. Now we have more and more devices that are connected to each other, that are connected to the wireless network, that are connected with Bluetooth. And this is the number of such devices as a function of the year. And what you can see is that it really exploded in the past years and it's going to continue growing. So this poses a problem. How do we handle such a huge amount of data? How, of all these big data, take what's the real meaning of it, take the essence, what's important, and disregard all those cat videos and all those things that are just noise. So one of these type of big data problems and problems that consist on taking the essence of a large number of bits is image recognition. So here you have 4 images, and if you remember, I don't know if they still do it, but to enter physical regulators, you have to choose the one that was a human. So it was this one in this case. So this is a big data problem because it has a lot of pixels with different grayscales. So if you feed this problem to a normal computer, which is very accurate and very reliable for many things, like for arithmetic operations and that kind of things, it will not be able to do it. And the reason is because traditional computers, they're built in a von Neumann architecture. And what that means is that you have your memory unit and your processing units are actually allocated in physically different places within the computer. So whenever you want to do some computation, you have to take data from the memory and you have to take it to the processing unit back and forth. That's what's called the von Neumann bottleneck. And the problem with that is that it really slows down the whole process and it makes it very energy consuming. And because it's a serial process, it makes it very prone to error. It's very error sensitive. So now you give this same problem to our brain, which is so much less accurate and reliable, and it will immediately tell you which one is a person, and it will even tell you the person that it is, and only using 20 watts compared to the kilowatts that many supercomputers use and are unable to solve this problem. And that is because the intrinsic architecture of the brain is completely different. It's built in parallel, and that makes it tolerant to errors. So the brain has a neuromorphic architecture that you have here in the schematic representation. So it is composed of neurons, and these neurons are arranged in layers, as you see here. And when one of these neurons gets excited, it outputs a signal and sends the signal to the next layer of neurons. And it sends it through these synaptic connections. So what you do is you send your input data to the first input neuron layer, and what you get at the output is that you get that data sorted. You get it classified. So to give you an example of how that would work in the case of image recognition, you have an image like this 4x4 pixel image that has different shades of gray. So you would input each of those pixels to each of the neurons in the input layer. So this black picture would be zero signal to one neuron. The white pixel would be maximum signal to another neuron. And then those neurons, if they are excited about some threshold, they would forward information to the next layer. So depending on the synaptic connections, these neurons here, they would be in charge of recognizing elements with higher complexity. So for example, this layer of neurons here would recognize if there is like a vertical line or a diagonal line or a circle. So the neuron that codifies a vertical line would activate. And the next layer of neurons would detect even more complex object. And eventually the output neuron layer would give you the final answer of who is that person. So the idea of neuromorphic computing is to try to use this neural network architecture and implement it in a machine. So how can we do that? So the easiest way to do it, the most straightforward, is just do a software implementation. You just take these neurons and synapses and you simulate them in a normal computer. And that might seem very simple, but it has been really revolutionizing in many, many fields, including science. It has changed a lot of directions of how the research is done in a lot of fields. But the problem with that, it has an intrinsic limitation, is that you cannot make very large neural networks. And this is an example why. So this, at least a year ago, this was the latest tower, the latest computer that was fabricated specifically to do machine learning, deep learning. And it used 10 kilowatts, it weighed over 100 kilos, and it's almost $500,000. And the size of the neural network that it can create is less, it's 7 orders of magnitude smaller than any mammal. So we are never going to get close to what we are able to do using this approach. So a more advanced approach would be to try to implement these neural networks in a hardware way. So you make circuitry that behaves that has the same behavior as neurons and synapses. And what you can do is you use a technology that you know very well, like CMOS technology. And for instance, that's what IBM did with the IBM 2 North, is their neuromorphic flagship chip. You have here a picture, it's a half a centimeter chip. And they can simulate 256 neurons, but for that they need over 1 million transistors. And the reason is that the transistors, they're not built with intrinsic properties. They don't have inherent properties similar to those of neurons and synapses. So you need a lot of them to actually implement those functionalities. So the more advanced solution to this problem would be what we are trying to look for when we talk about neuromorphic materials, which are materials that have the intrinsic functionality that neurons and synapses do, and that would allow you to make one neuron with only one device and one synapse with only one device. So these are two elements that we need to emulate. On one hand, we have the neuron. The neuron is an active element in the sense that it has to output a current. It does something called integrate and fire. So it takes the stimuli coming from other neurons, it adds all those stimuli, and then if it's excited about a threshold, it will fire. And it's volatile. After firing, it goes back to the initial state. Can you hear me? Because I'm here alone. Okay, I guess you can. So on the other hand, you have the synapse. Can you hear me, Ivan?
I can hear you, yes.
Okay, okay. Let's make sure because I don't see anyone.
No, there is somebody it has a problem with hearing, but they are looking into that, but I can hear you.
Should I? Okay, I continue. So on the other hand, you have the synapse. The synapse is a passive element. It doesn't have to output any energy. And the only role that it does, it controls the connectivity. It controls how connected two neurons are. And it's non-volatile. It has a memory. That's very important. So probably the most widespread way of, or the most, the way that more people are working on to try to search for neuromorphic materials is based on a phenomenon that is called resistive switching. So resistive switching, it's an effect in which you apply an electric field to a material and you can change the resistance of the material. And very conveniently, there is two types of resistive switching. There is volatile resistive switching that you can observe in materials that have an insulator to metal transition. And there is non-volatile resistive switching, which it's a completely different phenomenon, and it happens because of ion drift, because you can move actually defects or charged ions when you apply very strong electric fields. And here you have the examples. So this is voltage as a function of current for volatile resistive switching. So you can see that you apply a stimulus, a voltage or a current, and past some threshold, you can make the material become conducting, and when you remove the voltage, it goes back to the insulating state. So this looks a lot like what a neuron should do. And on the other hand, you have this non-volatile resistive switching in which you apply an electric field, you change the resistance, but when you go back, you don't go back the same way. So you have a memory. So that's what a synapse should do. So I'm going to focus now on this part, which is what has been worked on the most over the past decade, which is how to use this non-volatile resistive switching to emulate how a synapse works. So that's the memristor as an artificial synapse. So here you have, again, this is an IV of a typical IV of non-volatile resistive switching. You have this butterfly cycle in which you have two branches, a high resistance and a low resistance branch, and you can change from one to the other. And this is observed in different kinds of systems, but the ones that have been most widely reported are just transition metal oxides that are sandwiched between two electrodes. And the idea is that you have oxygen vacancies represented here by these red dots within an oxide matrix, which is this brown area here. And if you apply a strong electric field, you can actually move these oxygen vacancies, which are possibly charged, and you can make them form a filament that percolates between the electrodes, and that way you can change what is the resistance of your device. So you can see here a TEM image of how that would be. This we did in collaboration with the Gmail Zoo group at Brookhaven. This is a BO2 film that you have in here in between a bottom germanium electrode and a tall gold electrode. And after we perform resistive switching, you can see that there is this dark area here that you can see in dark field that forms this filament, which actually they did yields and they found out that it's a B509, which is conductive, and that's why you change the resistance. So you have this effect that you can change the resistance of material. You can, it has a memory, it behaves like what a synapse should do, but there is a problem, which is the following. So in a neural network architecture, you have that a neuron is connected with every other neuron in the following layer. And that's a lot of connections. In the brain, it's up to 10 to the 15 connections. So how do we achieve such a large degree of connectivity in something that you want to do on a circuit? So they quickly came up with this solution, which is to do what they call a crossbar array. So what you would have, how you would map this into something that you put in a chip is the following way. You would have these red squares here, which would be your neurons. This would be the neurons in one layer. And these would be the neurons in the following layer. And each neuron has this electrode that comes out of it. And wherever they cross the electrode of this neuron and the neurons in the next layer, you have actually this type of structure, in which you have a metal oxide in between two electrodes. And that would be your synapse. So at each connection, you would have a synapse, and that's how you are efficiently mapping this into this. So I'm going to show you how this was used actually to recognize patterns and things with some complexity. So let me show you this work. This is from 2015. And here's the type of crossbar array geometry that they use. It's very similar to this that I show you here. And they use this to do pattern recognition of these images, which are 9 pixels. They are 3 by 3 images. So each pixel, they fit to one of these 9 electrodes that you have here. And then what they do is they adjust the weight of each of these synapses of the crossbar array, so that the crossbar array is able to identify, for instance, this image would be able to, this architecture will be able to tell you if this looks like a Z, like a V, or like an N. It has 3 different categories. So what they see is that after, they keep training the network, and the more they train it, the less failures the neural network makes. So the number of misclassified patterns goes down as you train the neural network, and goes down actually below 1%. So the neural network can say, this looks like a man. And so this is a paper from 2015. If you go forward just 3 years, you can see the level of complexity, how fast the field evolved. So this is a paper from 2018, and here they are dealing already with wafer scale crossbar arrays that are very well integrated with transistors, so they can carefully adjust the weight of each synaptic weight. And in this case, they're able to take these images of handwritten digits. These are 64-bit images, 64 pixel images, and this crossbar array is able to take this image and say, okay, this is a 7, just a handwritten image. So they really have done a lot of work, but there are problems to this. And the problem is that you would be expecting a circuit like this, in which you have something that, something small that is your neuron, and you have these synaptic connections that are also small in the 10 nanometer length scale. But the real circuit is actually more like this. Because we only have the synapse, we don't have something that can act as a neuron. You're left with this type of arrangement in which you have a crossbar array here, which will be this thing where you have your synapses, but then your neurons have to be CMOS circuitry, which are digital. So you need a lot of circuitry first to adapt the signal between analog to digital, and then to implement the neuron. So what we can say is that only half of the job is done. In order to complete this picture of a scalable neural network that is done in hardware, we need neuristors. And that takes me to the following part of the talk, which is about volatile resistive switching, and more in particular, about how you can use it to mimic what neurons do. And what I'm going to show you now is about a lot more physics. So far it was just a review of the state of the art, more engineering-like. And why are physics important here? It's because there have not been that many works in this field. And in order to fabricate something, and in order to see if something is feasible, first we need to understand the physics of it. We need to understand, first of all, what's causing this effect, the mechanisms that are underlying, and other things such as the timescales or the length scales. Without that, you cannot even start. So that's what I'm going to be talking about. So this volatile resistive switching is observed in materials that have an insulator to metal transition. They're normally referred to as mod materials. And in San Diego, we work with probably the 2 most archetypical examples, which are B203 and VO2. So here you have resistance versus temperature. This is a logarithmic scale. And you can see that both have a first order phase transition in which the resistivity goes down several orders of magnitude. And together with this transition, there is a structural transition that happens at the same time. So these that you have here, these are X-ray diffraction, two theta scans at different temperatures. Blue is colder, red is hotter for B203 and for VO2. And you can see that the transition temperature, you have a shift in the black peak. So there is this structural transition that is happening together with the electronic transition. And there has been a lot of debate whether, maybe some people were saying that these transitions actually don't happen together, but they are decoupled. Somehow you first have a transition from metal to insulator, and then a few kelvins lower in temperature, the structural transition happens. That we did careful measurements, you can find them in this paper, and we track them, and we see that no, these 2 transitions are really well coupled, and they happen at the same time. So now you take one of these materials, like VO2 that we have here, and you pattern 2 electrodes, so you can pattern them very close together, so you can apply a very large electric field just with a few volts. So then you apply some current or some voltage, and you can you can do a voltage trigger insulator to metal transition, which is what you see here. The material is insulated here, and then you use it to go into the metallic state. So why is this happening? So the most straightforward answer is it's just happening because of your heating. You're just passing a current and you're heating up and you're going into the metallic state just because you're raising the temperature. But we discussed here, I won't go too much into this, that this is not the only mechanism. Actually, for example, in B203, there is a very strong direct effect of the electric field, which we see that can produce electric field assisted doping and stabilize the MOT insulator and produce a transition into the metallic state. But you can find the details here. So how does this look spatially? So I'm going to show you now a video. This video is just a collection of optical images taken with a microscope. This is a B203 film with two gold electrodes. These are the two bright things that you see here. And the video that I'm going to show you is just a collection of photographs that have been pasted together. Sorry. So you can see that when you go below the threshold, you have this filament that appears and connects both electrodes. And so this dark area that you're seeing here, this is B203, the same B203 you have outside, but because the metal and the insulating, they have different reflectivities, you see this contrast, you see it as a darker area. And so you see that as soon as we pass the threshold, the filament appears, it becomes wider, the more current you pass through it, and then when you decrease the current, the filament disappears. So this is a beautiful image, but you can see here that it's an optical image and the size of this device is 20 microns. And it doesn't illustrate very well what happens at the nanoscale, what happens when you look closer. And that's actually a key question because it's not very well known and it's fundamental because one of the main challenges that this type of resistive switching faces is that you fabricate two devices that are very similar. They are the same device. So one of them, for some reason, has 1 volt of threshold voltage and the other one has 5 volts. There is a lot of variability between devices. So to understand that, we need to look much closer. So what we did is the following experiment. We took a device very similar to the one that I showed you. You have here a representation. So it's a VO2 film in this case with two nickel electrodes separated 100 nanometers between them. And we took them to Argonne National Lab, to the synchrotron there, and there they have an X-ray nanoprobe that they can focus the X-ray beam down to a 30 nanometer spot. We did this in collaboration with the Spirko group. And then you can take the 2D diffraction map coming from that spot. And this is what you see here. So here you can clearly see the two peaks corresponding to the two phases, one corresponding to the low temperature monoclinic insulator and one corresponding to the high temperature rutile metal. So this allows you, with 30 nanometer resolution, to determine what is the phase fraction, how much metal and how much insulating you have at that point. So now if you raster this, if you scan this across all the field, you can make a 2D map of how much metal and how much insulator you have. And you can do that while you are performing resistive switching in this device. So this is what I'm going to show you here. This is a 2D map. You can see here in black line the nickel electrodes outline. So blue means more insulating, it's mostly insulating phase. Yellow means mostly metallic phase. So what you can see is that as soon as we pass the threshold voltage, we start nucleating some metallic phase. Here you can see this metallic area that appears there as a yellow spot. And as we increase the current that we apply, more and more spots are visible until we have this, that a lot of the device looks like it has undergone a metallic, it has gone the transition into the metallic state. But what you can see here is actually very different to what I showed you in the video. In the video, you had this nice filament that was clean, percolating between both electrodes. But what you see here is that when you increase your resolution by a factor of 50 or 100, actually the picture looks very different. You don't have this clean percolation anymore. You have these spots that actually are the same size as the grains in your film. You have this heterogeneous percolation between the electrodes in your device. So what this is showing is that the switching process is actually extremely dependent on the particular local topography of your device is. So you might have two devices that look completely the same, but just because the grain arrangement might be a little bit different, that is expected to have a very strong influence on how the switching will take place in your device. And that explains the big variability. So I'm going to move on now to a different topic, which is the dynamics of this voltage trigger insulator to metal transition. And this is an important topic to study because most of the work that has been done concerning this type of volatile resistive switching is DC. It's not studying the dynamics. And if you're going to use this for real applications, you want to do things such as neuronal spiking. You want to send pulses to your material, and hopefully you want to do it in the megahertz or even in the gigahertz regime. So it's really important to understand in the nanosecond timescale, things like how fast does your material go when you apply a voltage from insulator to metal? How fast does it go back into the insulating state when you remove the voltage? So to carry out that kind of experiments, we use a high-speed Prof station, and we send voltage pulses using a function generator to our device. And then we use a low impedance oscilloscope to take the current reading and see what is the dynamic response of the device. So this is what I'm going to show you here. So we send 200 nanosecond pulses to this type of device. And here you have current that goes through the device as a function of time. The pulse is applied at 0 nanoseconds. And you see that current raises a little bit, but not much, because the device remains in the insulating state. But if you increase the amplitude of this voltage pulse, what you see is that above some threshold voltage, what we call the threshold voltage, you're actually able to induce a transition into the metallic state. And you have that your material now becomes metallic and conducts, so the current goes up. But that doesn't happen immediately, and you can see that there is some incubation time. You have to wait some time between the moment you apply the pulse and the moment the device metallizes. And this incubation time becomes shorter as you increase the amplitude of this voltage pulse. So a similar important question is, okay, that's how it went from insulator to metal. How does it go the other way around? How does, once it's metallic and you turn off the voltage, go back to the insulating state? So we measure that. This is resistance as a function of time. This is the pulse is applied here, and at 200 nanoseconds, we stop the pulse, and you can see that the resistance of the material remains low for a few tens of nanoseconds until the device cools down, and then it shoots up because the device becomes insulated. So you can see that both the insulator to metal and metal to insulator transitions, they both happen in a time scale of around nanoseconds of tens of nanoseconds. So what this means is that as long as you have pulses that are farther away than this distance of a few tens of nanoseconds, they should be non-interactive, because that's the characteristic time scale of your the relaxation and how fast does it go into the metallic state. So to check that, we did the following experiment. We sent a voltage pulse that is above the threshold. This is voltage as a function of time. This is current as a function of time. So we send one pulse above the threshold. So it induces the transition. You can see here the device becomes conducting. And then we wait some time and we send a second pulse. And this second pulse is below the threshold. So it should not trigger transition. But what you can see is that even after 100 microseconds, it triggers a transition. This is a pulse that is only 60% of the threshold voltage, so there is no way it should induce the transition. And this 100 microseconds is 3 to 4 orders of magnitude larger than those characteristic timescales of relaxation that and cooling down that we saw. So what this is showing is that the system knows that it has been fired, and it keeps a memory that it has been fired that allows you to fire it again using much lower voltages. So to understand better this type of memory, this volatile memory that we did a systematic study. And one of the things that we did is we changed the delay time between these two pulses. And this is what you see here. This is the second pulse is 60% of the threshold voltage. And you see here the probability that it will trigger the transition as a function of the separation between the two pulses. So you can see that clearly as you separate these two pulses more and more, this probability goes down, but this is logarithmic scale. It goes down very slowly. And you have that 10 milliseconds, which is like 6 or 7 orders of magnitude longer than any thermal timescale of our device. You still have like a 5% chance to induce the transition. So it cannot really be cooling down, or it cannot be any RC charge time constant of our circuit because that's in the nanosecond timescale. So what can it be? So one of the things that we thought is like maybe for some reason we have some metallic domains that while most of the device relax into the insulating state, they are persistent. For some reason they are very long-lived and they stay in the device, and somehow they make it easier for you to trigger the transition again. So Marcelo Rosenberg in Paris did some, with his group, they did some resistor network simulations. And what they found is you have here, this is a 2D map of the electric field in the area between the two electrodes. blue means low electric field, red means high electric field. And what they found is that even if you have a small amount of residual domains, the effect of those residual domains in the electric field is very large because they can actually focus locally electric field. And even though your electric field is not close to the threshold field, locally it can get close to the threshold field because of the inhomogeneous, because it's inhomogeneous. So this is only, this was a hypothesis, so we needed to measure if this is true. We have some persistent domains that are very long-lived. So we needed a probe, something that, a proxy that allows us to determine what is the amount of metallic domains that we have. So it turns out that reflectivity is a great proxy for that. So this is reflectivity in VO2 as a function of temperature. And you can see that it gives you a really good contrast between the insulating and the metallic state. You can see the hysteresis of the transition and everything. So it is a very good indication how the reflectivity of your sample of how much metallic domains you have in a particular area. So what we did is we modified the experimental setup to be able to focus a laser down to a 3 micrometer spot here in between the oxide gap. And then we use a photodetector to measure reflectivity, and we measure the time-dependent reflectivity to measure the metallic phase fraction as a function of time when we send a pulse of current. So here, this is as a function of current, what is the voltage? This is the red line. You can see resistive switching and the reflectivity. And you can see that indeed, as soon as you induce the transition, you have a jump down in the reflectivity that keeps going down as you increase the current and your filament becomes wider. So it's a very good proxy to measure what is the amount of metallic domains that you have. So this that you have here, this is the metallic fraction as a function of time once you turn off the voltage. So you can see that the metallic fraction goes down as the material relaxes and goes back to the insulating state, but it doesn't go back exponentially. It follows a power law relaxation. So because power laws don't have a characteristic time scale, this extends for many decades in time and allows you to see this effect even up to the tenths of the millisecond time scale. So this actually is not unique from this system. This type of power law relaxation is seen in systems that have collective relaxation dynamics. And one way to understand this is maybe naively, you can think that the rate at which one domain relaxes is given by this energy barrier. And this energy barrier is proportional to the size of that domain. So you have a domain that is 5 times larger, it's going to take you, the energy barrier becomes 5 times larger. So when you have systems with strain, which is where you observe this power law relaxation dynamics, what strain does is that it couples together larger areas. So it actually, to flip these larger areas will cost you much more energy, and that's why you will have different relaxation rates. So let me show you, this is the distribution of metallic and insulating domains taken from this paper. In green is metallic, in blue is insulating. This is a SNOM image. And what you can see here is that actually, and this is very typical from first order phase transitions in the regime, in the phase coexistence regime, is that you don't have any characteristic length scale. There are domains of all possible sizes. So that means that no scale in the structure would explain why we observe no scale in the dynamics in our case. So I'm going to move on to the next topic, which is how can we use this thing that I showed you, this the phenomenology of the voltage trigger insulator to metal transition, to do something that could be useful for neuromorphic computing, which is an heuristic, something that can mimic, can emulate a neuron. So let's just go over again what a neuron should do. So a neuron should be active. So it should output current. It cannot be just a passive element. And it has to be volatile. After firing, it has to go back to the initial state, has to do the integral fire. And I add another functionality here, which I will go in depth later about it, which is rate coding. So how do you implement a neuron? So this is a characteristic circuit schematic, circuit representation of a neuron that you see in many textbooks. And you can see that it's composed of 2 different blocks. So in one hand, you have this block. This is the integrator, the integrating block. So this block takes the inputs coming from other neurons, and it accumulates the charge in this capacitor. And when it's above some threshold voltage, you can induce this firing stage to create an output spike. So following this type of visual representation of a neuron, it's possible to construct CMOS-based circuits that have that replicate this type of behavior. There is a very nice review by Indivetti, in which he goes over all these different type of approaches that you can do with CMOS to create this type of circuits. And here you can actually see a micrograph of one of those CMOS-based neuron. So just to remind you, currently non-volatile resistive switching, the one that you would use to emulate synapses, they're able to do it with a characteristic scale of 10 nanometers. So you can see that the scale here is much larger. So clearly you are wasting all that scalability by using this type of approach. And the reason why this needs to be so big is these white areas that you see here. These large areas are the capacitors that you need to actually integrate the charge. So what this shows is that this capacitive approach is not scalable. So we need to come up with a different approach to do integrate and fire that is not based on accumulating charge on this capacitor. So there's actually two pretty recent proposals about alternative approaches, particularly this one, in which they use phase change materials. But these approaches, they fail to make active elements that are volatile. So what we propose is doing a different approach, which is based on thermal integration. So in our case, we would have a resistor that would act as a heater, and that would be the integrator. So you send current pulses to this heater, and each current pulse is going to elevate temperature a little bit more. And then you have a firing stage, which is very sensitive to changes in temperature, which is electrically disconnected, but is thermally coupled to this heater. So there is very good thermal transfer between both of them. So when this is excited about some temperature threshold, it outputs a spike. And in our case, for this temperature sensitive firing stage, we decided to use VO2 because it has this really, really sharp dependence with temperature. So we actually fabricated a proof of concept device that you have here. This is an SEM image of the device, and this is a schematic representation. So this device consists on two titanium gold electrodes that are at the bottom. You can see them here. And there is a gap in between them. There is a VO2 gap, which would be this element. And then on top of it, there is this stripe, this contact that would act as a heater. You can see it here. And in between, there is this aluminum oxide barrier, which would be an electrical insulator, but it's a good thermal conductor. So the idea is that we are going to bias this gap very close to the firing point, very close to the threshold voltage, but below it, so that any current spike that we send through this heater is going to be enough to push the system past the firing point and make it fire, make it go into the metallic state. And this is actually what you see here. This is the current as a function of time. In red, you have the input current represented in this axis. And in blue, this axis, this is the output current of your device. So we send a pulse to the device, and you see that we can make our device spike. So you have spike in, spike out, which is what you should get, what a neuron should be doing. So importantly, this is current that our device is outputting through this electrode. So it's an active device. It's outputting current. The pity about is that when we started doing this project, the idea was that we were going to get an output that was going to be larger than the input. That, this was going to be biased close to the firing point so that any stimulus coming from here is going to be enough to create a much larger response so that the input would be smaller than the output. And that is very important because actually, if you want to use only this device, you don't want to use amplifiers or anything else. You want this as a neuron. If you need to amplify your signal, that's more circuitry. You're losing the scalability. So unfortunately, we were not able to get an output that is larger than the input, but there is no reason why we shouldn't get it. And actually, we are thinking of ways that we can achieve that, getting a larger output than the input that would make a standalone component that can be used as a neuron. So it's active, it's volatile. So what about the other functionalities, integrate and fire? So integrate and fire, when you are doing capacitive integration, the characteristic timescale of integrate and fire is given by just the RC constant of your circuit. In our case, it's given by the characteristic thermal time of our device, which is given by the specific heat. So here you have what is the warm-up time, how fast does the device warm as a function of the input current. You can see that it's always around 100 nanoseconds. So as long as you're working with those frequencies, you should see integral amplifier. And this is actually what you see here. And here you have the input as a function of time. This is the output as a function of time. None of these spikes has the strength by itself to induce firing in our device. By the cumulative effect of all these spikes eventually leads to to an output, to a spike in the output. And finally, what about rate coding? So rate coding is the way in which neural networks codify the intensity of signals. So actually, when you're looking, let's say you're looking at a light, the way in which your brain knows if that light is strong or is a weak light is by the frequency of the spiking. So a strong stimulus, a strong input will cause fast spiking, and a weak stimulus will cause slow spiking. So actually our device also has that. Here you have current as a function of time, and here output as a function of time for two different inputs. So we send a DC input, different amplitudes. So you can see that when the amplitude is 5.3 milliamps, we have this spiking, but if we increase the amplitude of the input, you have a much faster spiking, which would be rate coding. And actually here you have the firing rate as a function of the DC input, and you see that we have this clear rate coding characteristics. So with this, I'm going to move to the prospects. How is this continuum? Where to now? So one of the things that we observe in this type of material in vanadium oxides is that you can actually observe both types of resistive switching. So when you're at low temperature and you can apply a strong electric field and you have high resistance, you actually can induce the motion of oxygen vacancies and you observe non-volatile resistive switching. And when you're at a higher temperature or lower resistance, when you're closer to this transition, you actually have volatile resistive switching. And that is very interesting because that means that in the same material, you could have both synaptic functionalities and neuronal functionalities. And that gives us a hope. Maybe we can, in the same film and at single temperature, implement both. So we can make a neural network in a single film in the same material. So in principle, it would be possible to do that if somehow you're able to move the position of this insulator to metal transition. If you are able to locally change where this transition is, you can bring it to lower temperatures. In principle, at a single temperature, you could have some parts of your film that are behaving as a synapse and some parts of your film which are behaving as neurons. But for that, we have to be able to tune the insulator to metal transition locally. So we are looking at different approaches for that. Maybe the most promising one is using radiation damage. So actually, radiation damage is very effective to control this insulator to metal transition. Here you have resistance versus temperature in VO2. You can see the insulator to metal transition, and you can see it for different doses. These are ions per square centimeter. You can see that as we increase the irradiation, these are oxygen ions, as we increase the irradiation to our film, we can not only reduce the amplitude of the transition, but also move the transition temperature low to lower temperatures. So one possibility would be to use a focused ion beam to locally irradiate your film, maybe less than a micron, resolution better than a micron. So you can locally, for example, choose to have this type of transition. So you can write where you want to have synapse and where you want to have a neuron. And another approach is using a strain, in particular using piezoelectricity. So we did this experiment in which we grow a B2O3 film on top of a ferroelectric, in this case PMNPT, and what we observe is that if you use a gate to change the ferroelectric domain configuration, that you can see here, this is in this case totally out of plane, in this case you have a lot of in-plane domains, you can actually strain a lot your film, and because these films are so sensitive to strain, you can move a lot with the position of your transition. So with this, I'm going to finish the talk. I've given a review of what neuromorphic computing is and what is the state of the art right now, more or less. And then I've shown you what our research in the field is, in particular, the voltage trigger insulator to metal transition. I've shown you what is the spatial distribution, what are the characteristic length scales of this transition, showing that it's actually very homogeneous when you look close enough. I've shown you that the dynamics are very rich of this voltage trigger insulator to metal transition, and actually the material keeps a memory that has been fired that deeply affects how it's going to respond to subsequent voltage pulse. And I've shown you how that you can use all that to actually create something that can emulate a neuron. And there is a very hopeful outlook in which we can use this type of material and this phenomenology to implement both synapses and neurons and have a whole neural network hopefully implemented in the same field. That's it.
Okay, thank you very much. This was a great talk. So now I think we will celebrate eventually with a bottle of this favorite wine of mine. Okay, this bar mitzvah and this talk. And now it is Roldolfo's turn to answer questions.
Yeah, there was a question by Günther Gutterod, but I couldn't find it. Wait a second.
Roldolfo, you have to turn on the camera.
Yeah, well, the camera it's turned up, but you have to move this, remove the presentation.
Okay. There.
And then there seems to be some questions. Someone raise your hand.
And there is 3 hands. 4.
Gonzalo, is anybody raising their hand? Can you check that, please? Gonzalo?
Yes.
Well,
Yeah.
So
We have 4 people raise hand, and
could you give them?
yeah.
Let me see if I could find it.
Yeah. It's in.
Could you give them the possibility to ask?
I think that you have to.
No, it's not showing here.
There is a question in the questions and answers.
Yeah, well, someone, Gaston Garcia, asked that you have report on the focus ion beam implantation to fine-tune the system. Will deep implantation that is at higher ion energy bring up additional possibilities?
Yes. So actually, what I show you that let me share my screen again. These that I'm showing you here, these are done at high energy. We have done oxygen and helium irradiation. I think it's in Strasbourg, but I'm not sure. And these are 100 kilo electron volt ions. So this is high energy, in which the ion just pierces, it goes through the film without getting implanted, just creating disorder. But whenever we do it with Phi, which is lower energy, and it's gallium ions, we get a lot of implantation. Actually, gallium gets implanted in the field, and the results are actually very similar. We actually didn't publish this yet, but the results are very similar to what you see with high energy. So in principle, both of them would be an opportunity.
Okay, then Juan de la Figuera also wants to talk, so I'm going to give them the chance to ask. Juan?
Is this working?
Yes.
Okay, that's impressive. Okay, yeah, I had a question. So the VO2 films you are using so far, are they polycrystalline? So are they grown by sputtering or MBE or?
So they're grown by sputtering.
Okay.
They are textured.
Yes.
Yeah,
okay, so the question I wanted to ask is, what is the role of the grain boundaries in the films? Do you need them? Would you be better without them?
So actually, so we also grow in, so these films, I didn't mention it, they're grown on aluminum oxide, on sapphire. And that's where they grow grainy, and that's where they grow texture. We have also grown these in titanium oxide, in titanium oxide, VO2 grows epitaxial and much better film quality. Actually, that doesn't mean that the insulator to metal transition is better. So the presence of grains actually makes it easier, because when you have the transition, you don't only have the electronic transition, you have a structural transition. So very epitaxial films actually are very strained, and they have a lot of trouble undergoing that structural transition because of strain. Strain is impeding them to expand or to contract. And we see that with B2O3, when it grows on aluminum oxide, it grows epitaxial, and for some cats, it completely suppresses the insulator to metal transition. So, contrary to intuition, you don't need to have perfect epitaxial films. Very grainy films with a lot of defects might actually have much better transport properties than those films that are grown epitaxial.
Okay, thanks a lot.
Javi, there is another question by Cynthia Quintero. You have to turn on the microphone. Okay.
Good morning, afternoon. Thanks for the talk. My question was regarding the thermal budget, because at least I am referring to the slide in which you were showing the optical image in addition to some current versus voltage curve. And if I understood properly, the current was about 10 milliamps or so, and the volt was quite high. So the power consumption is really high. My question is, if you're considering reducing this consumption somehow.
This one, can you see it?
I think it's coming. There, that one.
So yeah, you're right. So this is a very large device. This is a 20 micron device that was fabricated ex professo for this application to be able to use an optical microscope. If you reduce the size of your device, you can go to 50 nanometers, and then your power consumption goes down a lot. It goes down to the nano watt. And actually, when you're doing pulses and when you have spiking, you might have 10 nanosecond spikes. So for B2O3, the energy consumption per spike, it goes down to the femtojoule. It's only like tens of femtojoules. Because for B2O3, I didn't go into that, but it's an electric field trigger transition. It's not triggered by joule heating. With VO2, you probably would have higher consumption, but it would still be well below or around the picojoule. So it's not a lot of consumption.
Okay, so it depends on the geometry and the size.
Depends on the size. Yes.
And if you don't mind, I have another question regarding it's a little bit connected with what you were saying about radiation and the fact that you have grain boundaries. So it's like a double question. The first one is, I don't know if you have considered reducing the energy by just using some sort of piece of layer that can slow down the energy in such a way that you get implantation. And the second question will be if the fact that you have grain boundaries will not make you some channeling effect, such that you will have some improved, let's say, transmission of the species that you are aiming for modifying your structure.
So you're saying, so the first question was that if you put some sort of layer that would slow down the ions so I get more implantation?
Yeah. So, I work at some point in an accelerator facility, and what we usually do is just to put a metallic layer in front of your sample. And depending on the thickness and the material of your piece of material, you can slow down the species, and you can tune, let's say, the energy of the beam that you get on the other side.
Okay. Yeah, we haven't done that. It's an interesting possibility. So we get quite a lot of implantation with gallium, actually, with using lower energies. So, but to be fair, we don't understand very well this process we still don't understand when you irradiate these films. if you are just doping or if it's the effect of disorder, the one that plays a major role, if it's important at all that you have implantation or not. We don't know if it's important, because when we do this with high energy helium, there's no implantation, and we get very similar effects. So to be sincere, we don't understand very well yet why this is happening. We know the phenomenology. And regarding the question about the grain boundaries, that we also don't understand.
Okay. Okay, thank you.
There's another question by Lucia Valle. Lucia, turn on the microphone, please.
Hi, am I on air?
Yeah, sure.
Okay. Thanks for the talk. It was fantastic. I have a question regarding timing. So this is, I mean, 10 nanoseconds of time or 100 nanoseconds is still relatively slow. Are you looking at other systems that can do the transition really fast? I mean, I guess ion diffusion is more limited in the time scales, but at least the transition, what do you think? What would be the fundamental limit?
So, okay, so there have been the studies that are normally, there are many studies about how fast you can induce a transition from insulator into metal, and they talk about femtoseconds. Those are all optical studies. So electronically, you can go faster, but not much faster. Like, it will be very hard to go below 100 picosecond. In our computers themselves, they are limited by that. So we are interested, of course, in how fast you can go from insulator to metal, but we're interested particularly in how fast you can go by applying a voltage, not by a pulse of light or anything like that. So that limits the speed, the maximum speed that you can actually observe, which is normally half a nanosecond. That's normally electronic circuits are like limited to that. You can maybe bring it a little bit down with better prototyping, but you're limited by the RC constant of your device. So you cannot go much faster than that. Ion diffusion, yeah, it's slow, but it depends a lot exponentially on the amplitude of the electric field. And these devices are very small. In non-volatile resistive switching, the thickness of the film sometimes are around 10 nanometers. And resistive switching there has been shown to be as fast as 1 nanosecond in non-volatile resistive switching. In volatile resistive switching, it can be as fast. We measure as fast as our time resolution of our setup was. The material was faster than us. So I don't think there is any limitation other than just the limitation of your experimental system, the limitation of your wires, which have an intrinsic capacitance that you cannot defeat.
There's another question by Professor Salvador Ferrer, and the question is, the conductive filaments in the oxide presumably are charged anionic vacancies. Then likely a buildup of charge will occur, producing a bias against the applied field. Is this a correct picture?
So just to clarify, the filaments that I've shown of our research, they are not caused by oxygen migration. They are just metallic because there is a part of the material that undergoes the insulator to metal transition. But in the case when you have non-volatile resistive switching and you have filaments which are formed of oxygen vacancies that you have moved, I would say no, that's not a correct picture because your filament is conducting, so you are evacuating the charge. So you don't have, the net charge would remain zero in the area around the filament. Even though the species that you're moving are charged, you will have screening because you don't have a perfect insulator.
I'm not sure whether Professor Gunther, you were trying to ask a question. Are you there? Because I saw you raise your hand, but then you remove the hand, so I'm not sure.
Cannot turn on the microphone.
Yes, I have. Okay, coming back to the filaments, how many times can the device go through the switching events? There must be some fatigue.
There is indeed some fatigue. So we've done up to 10 to the 12 cycles of 1 microsecond. Mm-hmm. And we start seeing some fatigue, but it's not very strong. So 10 to the 12, I don't know if that's a lot or a little. There is some fatigue, that is for sure. It's not important. It won't destroy your device after 100 cycles. Mm-hmm. But there is some fatigue, yeah. We don't know still that fatigue, what we think is happening is just because you're applying a lot of current, you have a thermophoresis, because you are repeatedly heating up, you have diffusion of oxygen out of that area. But it might be related to the structural transition, because you are going between two structures that in the end creates dislocations, and that's the source of fatigue. So it could be those two things. We don't know for sure.
Okay, thank you.
Yeah, there's another question here. Lorenzo Fratino, could you turn on your microphone, please?
Yes, so I have just a suggestion, an idea. In the beginning, you talked about the collaboration. You show a picture with Xiaobo Cheng that demonstrated that there is another transition in VO2 and at much lower temperature. So around 150 Kelvin, we obtain 509. I want to know if you think we can adapt your idea of making a grid of temperature in order to have a more volatile effect at high temperature and non-volatile at low temperature, in order to have synapses and neuron in the same material, just through a gradient of temperature.
Yeah. Just a question. So, which transition are you referring to? Which lower temperature?
In the beginning, Xiaobo Cheng.
Okay.
The one of V509.
Okay. So just in reality, what's happening there is that you are making. Let me share the screen. Here. So in reality, what's happening is that the V509 itself, it's also a correlated oxide, and it also has an insulator to metal transition. So when you actually create these filaments, you see two transitions. One is the bulk VO2 that is undergoing the transition, and then at lower temperature, you see the V509. So yes, that you comment, the thing that you comment, it would be possible. You could find a temperature range in which the V509 would be. Yeah, you could find a temperature range in which you would have this insulator, but it's still metallic, and at lower temperatures, both of them would be metallic.
Exactly.
Yes, that in principle would be possible. The only thing that would worry me is that the variability between different cycles, because creating these filaments back and forth might be easier, but making them have an insulator to metal transition, I'm not sure how reproducible that is, if you do it several times. But I'm not sure about it.
There is another question by Mariela Mengini. Mariela, please turn on the microphone.
Yeah, can you hear me? Yes.
Yes.
Yeah, okay, thanks for the presentation, Javi, it was very nice. I have two questions. One is related to what you were talking before about, we're discussing before about the power consumption and, reducing the size and all that. So the ultimate, I guess, solution would be to have vertical type of structures, right? Because you will have the shorter separation. So my question was whether you have tried that. I mean, in the sense that you don't need epitaxial films, I guess that is not a big deal, I guess, for growing the films. And the other one is, maybe I missed that, but you show the firing rates of the neuron as a function of the amplitude of the input. And I was wondering if you also have such analysis as a function of the time between the pulses, and if it is the same type of response, let's say, as either amplitude or time.
Okay, so regarding your first question about the vertical devices, yes, so the problem with this is that even though you don't need an epitaxial film, you still need a good quality film. So you need to go at high temperature, like maybe 600 Celsius. So the problem with doing a vertical device is that if you want to put a bottom metallic electrode, it will diffuse immediately, So one solution to that is using germanium or silicon doped, heavily doped germanium or silicon substrates. And we've done that. We've grown over whole doped germanium, and we get nice films. We have a 2 order of magnitude insulator to metal transition. But that's recent. The problem behind with that is that there is this germanium oxide layer that forms. and it increases the resistance of the whole vertical device. But yeah, in principle, it's possible. There have been reports of you can grow on germanium.
Okay.
And regarding your second question, just a second, did I go there? Okay, so here, you're talking about this graph, right?
Yeah.
So you see here that we are applying a DC input. So no, we didn't do that analysis because we are not applying pulses, you know, to see this rate coding.
Okay, it's just the, yeah. But then it's the other one, but you can do similar analysis, right? For the one that you have, this refractory peak, yeah, this one.
Here, the internet,
right?
yes, this we have done as a function of the input amplitude and the input pulse separation.
Okay.
I don't have it here, but it's in the paper. If you read the paper,
okay. Yeah, thank you.
So I don't see any more hand raise or a question. Is there anyone else that want to ask something? Javi, can you remove the your screen?
Yeah, there is another question, I think.
There's another question by José Luis Cuñado. That's right. Turn on the microphone, José Luis. Turn on the microphone, otherwise we cannot hear you. Yeah.
Now?
Okay.
Okay. It's because I'm new on this kind of event.
Well, we are all new.
Yeah. I wanted to ask how critical is the size of the gap between the electrodes in terms of if this can influence the onset of the metallic filament, and if this has some influence in the pulse length that you can use to induce these states, these filaments. And that was my question.
Okay. José Luis, you see kind of the same phenomenology through very different sizes of your device. So we've done devices from 50 nanometers to 50 micrometers, and more or less the phenomenology is always the same. The thing that changes is that the larger your gap is, the higher the voltage that you have to apply. So for a 50 nanometer gap, you need maybe 1-2 volts. You need like 50-60 volts for a micrometer, you know, for several micrometers gap. Your energy consumption goes up, but the rest is the same. We observe the same type of phenomenology. It doesn't change the physics much.
And another question is, the filament is formed all of its length at once? It covers the gap all at once, or somehow it's formed in one of the contacts and then it travels towards the other one?
So we actually have a paper that we'll submit soon in which we analyze this type of questions. So unfortunately, we haven't been able to resolve how the, you know, like a lightning bolt, right? How like does it grow from here into the other electrode? But what we have resolved is once it grows, how it thickens. So what we see is that actually the thickening is very fast as soon as you have connection. It starts thickening very fast at the beginning and it slows down. So the initial thickening is in the order of 1 microsecond, or for micrometer size devices, and then it slows down over time. But no, we haven't captured the moment in which it leaves one electrode and it goes to the other. That would be beautiful, but it's a very hard experiment, because I think that's a very, very, very fast process, and it might not be easy to capture it with, for example, reflectivity techniques.
Okay, thank you very much. And sorry, I forgot to tell you that the talk was very interesting and I liked it a lot. Thank you.
There is another question here. Xiaobo Shen, please turn on your microphone. Okay.
Hello, Javier. Very nice talk. I have a question. So your VO2 thin film are basically polycrystalline. There are many grains connecting the electrodes. So I was wondering whether the grain boundaries are more conductive or less conductive compared with the VO2 grain itself.
So that is the suspicion. That is what it's always reported in literature. That is, but we haven't measured that, so we don't know. You would expect that just because the boundaries are more disordered, and in general disorder lowers the transition temperature, that yes, that the boundaries would be more conducting than the bulk of the grain. But it hasn't been measured. No, I don't think anybody has measured that. It has been seen that for ion drift, when you have non-volatile resistive switching, the boundaries are way more mobile. You have way higher mobility to push ions through the boundaries that you do to do it through the crystal, to the bulk of the grain.
Okay, thanks.
Thank you. Anybody else? It seems that no, I don't see any more raised hands or comments. Then I would like to thank Javier, of course, for this first talk, but just let me show you the idea behind is not just to have this one seminar, but to continue with this colloquia and adding topics which are at the frontier of nanoscience in the next month or so. Every 2 weeks, more or less, we will announce this thing in time. We will have talks on certainly interesting topics, such as shown here. And let me show you larger size. Some of them controversial, like the twisted graphene bilayer, so much loved by Ivan. But I would also like to show you that we will cover a wide range of things, not only of physics, but covering also chemistry and biology. And in particular, I would like to call your attention to the topic of adding physics and biomedicine on the fight of on this virus that is hitting so hard the world. So these will be some of the topics that we will be covering in the next month, as I said, and well, very soon we will give you the names of the speakers and the exact order of the different talks. So keep tuned to this Frontiers of Knowledge colloquia, which I think are very interesting. So thank you, Javier, and it was a pleasure to have you around and see all
it was a pleasure for me.
Exciting things.
Thank you for inviting.
And of course, I would like to thank Gonzalo in particular and Bonnie for taking care of all this mess initially, which I think we handled rather well after all. And thank you, of course, all of you that still remain listening to this talk in spite of being very late, almost late in the evening in some cases. So we would like to close this thing now and thanking you, all of you. Ivan, you want to add something?
No, I'm very happy, and I think that this was a great start, and I hope that this will continue the same way, with the same excitement. I'm looking forward to it.
Good. So thank you, and thank you, Javi.
And I'm happy that you have had a bar mitzvah finally, that you have become an adult. Okay.
Well, okay. So thank you, and then we could close this.
Bye-bye.
Bye-bye. Thank you all.